How's it going? Back with another video of Chem with Com. Today we're going to do the last part of solutions and empirical formula, and that's going to be the empirical formula. All right, so um, first part is percent composition. Sorry, spaced out there. We're going to revisit this again, this percent equation that we used all the way back in topic 2. So let's take a look. It's going to be the part over the whole times 100% equals the percent of whatever that part was, right? Let's do a sample question. So let's say a sample contains 1.2 grams of zinc and 0.7 grams of oxygen. We don't know what it is. We don't care what it is. We just know that's the percentage, right? That's all we know. And they're asking what the percent is of each component. So if we look at the part in whole, right? The whole thing is the zinc and oxygen, right? The part is whatever we're choosing. So if we want to find the percent zinc, we will put zinc here. If we wanted to find percent water, we will put water here. But this has to stay the same because this is the total of the stuff we're looking for, and that's this part here. All right. So to find the percent zinc, you're going to just put zinc into where the part is, which is called the numerator. And then on the bottom isn't the oxygen, it's those added up. So 1.2 grams of zinc plus 0.7 grams of oxygen, right, is going to be 1.95 total grams of the whole thing, right? Zinc and oxygen. So we do 1.2 grams divided by 1.95 grams. The grams cancel out, right? And then we're left with 62%. And we have two sig figs because here there was one decimal. So this should be one decimal. So this is where the sig figs ended. So that's 2 digits, 2 digits, 2 digits, 2 digits. So we should have 2 digits in our sig figs. All right. So again, add up the totals, just like we did mass percent, right? We had to find out the solute and solution. We added those up. To find the percent oxygen, you would just repeat that with the 0.75 grams of oxygen instead of the 1.2 grams of zinc. Alternatively, you could take 100% because you only have two things in this mixture compound, right? Zinc and oxygen. Together, those make up 100%. So if we took 100% and minus 62% or subtract 62%, that's going to give us 38%. And that would be of the oxygen because this is the zinc. This is zinc plus oxygen. So that would be another way to do that. I think it's quicker. Do not use your percent button on your calculator. You shouldn't have one. If you have one, you probably have the wrong calculator. You want to treat the percent sign like a variable, right? Here, right, there was no grams, the grams canceled out, but we multiplied the 1.2, sorry, we divided the 1.2 by 1.95, divided it by that 100%. That percent sign carries over, right? So treat it like a variable and you'll be all good. All right, let's do something else. Let's do a actual problem here. It says a 24.81 gram sample of a gaseous compound containing only carbon, oxygen, and chlorine is determined to have 3.01 grams carbon, 4.00 grams oxygen, 17.81 grams of chlorine. What is this compound's percent composition? All right, so we know the total. That's the whole. We'll write it over here. Whole equals 24.81. So let's set this up for carbon, oxygen, and chlorine. All right, so everything's going to be the same for the denominator and the 100% because this is all the percent calculations. We know the total for the whole thing. Gram, 24.81 grams, 24.81 grams. This is, we're going to have to change it up. 3.01 grams of carbon, 4.00 grams of oxygen, and then we have 17.81 grams of chlorine. So let's just go do the math. I'm gonna pull up my calculator. Let's see, where did I put that? Over here. Guess I don't have it open. Let's see. Free online scientific calculator. There we go. Must have closed them all. All right, let's take a look. 3.01 divided by 24.81, I believe. 3.01 divided by 24.81 times, oops. So we have to, see how it's set up there? It says divide by, we want to multiply the whole thing by 100. So we have to move the mouse over, or move the cursor over a little bit. So it's going to be 12.13. Let's take a look. So 3 sig figs, 4 sig figs, we need 3 sig figs, 12.1. And that's going to be percent, and specifically carbon. All right, next one is 4. Let's use the other calculator so we can go back and forth so you can see this. This is how I like to do this calculation. It's going to be 4. Oops, sorry. Close up some of this here. All right, so clear this. It's 4. You don't have to put the .00 in the calculator if you don't want. 24.81, and I say enter, times 100. Enter. 16.122. So 3 sig figs, so 16.1% oxygen. And then this is 17.81 divided by 24.81. So let's go back to here. 17.81 divided by 24.81. Move the mouse over, times, sorry, not the mouse over, move it over a little bit. 71.79 because we have to round up. So it's going to be 71.79 because we had more digits. 20. I already forgot. 71.79. Sorry about that. 71.79% chlorine. All right. Cool. So again, part over the whole. We're going to do this over and over again, right? Nonstop for the rest of your science careers. All right. So now, how do we get percent composition from chemical formula? All right. So we're going to use the same equation. This one, we're going to look at percent hydrogen in water. So as soon as you see percent, yeah, okay, percent equation, hydrogen in water. What does that mean, right? So the whole thing is going to be the water, H2O. Here, it's just 2 H's, right? On the bottom, it's 2 H's plus 1 oxygen. So we're going to look at the hydrogens, put it here. We're going to look at, see the red box is the whole thing. So yeah, all hydrogens on top, the whole molecule on bottom. Percent hydrogen is going to be what we're going to calculate. So if you look here, we have the 2 hydrogens. Here we have the 2 hydrogens and the 1 oxygen times 100%. And so we find the periodic table, we find the 1.008, we fill those in where the hydrogens are, grams per mole. And then this one we just put down below in the denominator where the oxygens are, right? 2 hydrogens, 1 oxygen, right here are just two hydrogens, right? Because again, the formula is H2O. We're trying to figure out the percent of all of the hydrogens, not just one hydrogen, but all of the hydrogens, right? So you do that math, you get 11.19%, and that gives you your percent hydrogen in water. All right. To find the oxygen, you would just repeat with one oxygen instead of the two hydrogens on top, right? You would just substitute this part here, and that'll give you the percent oxygen. Alternatively, you could do the trick we did on the last couple slides. You could just take 100%, both hydrogen and oxygen, and subtract that 11.9% hydrogen, and that'll equal your percent oxygen. All right. So you can pause this, rewind it, do whatever you need, but we're gonna try this right now. All right. What is the mass percentage of iron in the compound iron oxide? And they actually tell us they want 3 significant digits, so it's kind of low effort on our part. We just do what they're asking. So let's try it. Let's figure that out. What are we looking for? Well, it's iron. 3. Oh, sorry. You look here, there's 2 irons, right? So 2 times iron. The whole is 2 times iron plus 3, because we have 3 here, times oxygen. Let's set that up. So part over the whole times 100% equals percent iron. Okay, so let's do that. 2 times 55.85 over 2 times 55.85. Sorry, let me make sure this is complete. Shouldn't be just that. It should be grams per mole, right? We need our units to be proper and get this to work. And this one is 3, so 3 times 16.00 grams per mole times 100% equals percent. All right, let's take a look. We're going to do this all in one operation, and let's see how it goes. Okay, I'm going to clear this. We're going to say, watch the parentheses, 2 times 55.85, close parentheses, divided by, I'm going to have 2 parentheses here, 2 times 55.85, right? Close parentheses, a plus, open parentheses, 3 times 16, 2 close parentheses, and then times 100. And we get 69.94. We need 3 significant digits. It's going to be 69.9%, specifically iron. Right? And if we wanted oxygen, we just do 100 minus 69.9, because this is iron plus oxygen. We're subtracting out the iron. What's left over is just going to be oxygen. 100 minus 69 is, 70.1%. Right? Oh, sorry. 30.1%. Woo! Almost had to redo the video. All right, let's continue. We're going to jump into something a little more difficult, but not by much. It's everything we've done before. There's just 1 or 2 steps at the end we haven't done. So we're going to now determine empirical formula. So the brief review, we just talked about empirical formula is, but let's hear some definitions. It's the same ratio of atoms as the molecular formula, but lowest subscripts. So something like H H4O2 would be H2O. Something like N2H4 would be NH2. Something like CH3 would be CH3, right? Because you can't get any lower ratio than that. So empirical formula showing the composition of a compound giving as the simplest whole number ratio of atoms, right? And this is the ratio. This is 4 to 2, which is also the same as 2 to 1. And this is, 2 to 1. This is also 2 to 1. This is a 1 to 3. This is a 1 to 3, but we can't get any lower, right? So that's empirical formula. All right, some chemistry experiments will allow us to determine the mass or percent composition of a substance. From this information, we can calculate empirical formula. Mg and O means there is one magnesium atom and one oxygen atom. This is what's called the mole ratio. Oops. Let me just fix that. That was bugging me. There you go. All right. So there's one magnesium to one oxygen atom. That's the mole ratio. In order for us to calculate the empirical formula from mass for percent data from a chemical experiment, we must first convert the mass or percent data to moles. So again, grams to moles. This doesn't go away. We're going to do this a lot. You're going to do this in your next class, your next class, your next class, right? So you got to get used to this. All right. This is the same kind of little table I set up for you guys to do it. So if you're going from grams to moles, you're going to cross this first arrow. The first arrow says use the grams per mole from the periodic table, right? So you're going to look it up. Here we would look up the mass for magnesium, the mass for oxygen, add those up, and we would use that as our conversion rate because it's that much grams per that many moles. So that's a conversion rate. So you could use that to convert to moles, all right? This is the book way to do it, which is fine. It's not very descriptive, and I like doing things a certain way. You don't have to do it my way, right? I recommend my way. I think it works all the time. Um, but yeah, so this goes, you want to go to mass to moles, right? This is converting from grams to moles. Then here you're going to divide by the lowest number of moles to get your mole ratio. And then you can convert to your lowest whole numbers. It looks simple, but it leaves a lot of stuff out where it's not super intuitive. So I was very descriptive on my way of doing it. It's a lot of words, I know, but it's complete. So if you're starting with percent, you have to change to the mass. All right. And once you're in mass, you can convert to moles, just like we talked about. Right. And so, boom, we're halfway done. Now, what we're going to do is write it a specific way, right? Write it with your first atom and then in little subscripts, moles of, oh, sorry, right here. Moles of what it is. We're used to seeing stuff like H2O, which we're going to get to, or NO2, right? But we're going to get to those whole number ones on round number 5, right? So write them as these little decimals or whatever numbers they come up as. Divide both moles of both elements. So divide the moles of both elements by whatever had the lowest moles. So if you look here, this is 0.2, this was 0.3. So we're going to divide both of these by 0.2055. And let me think I was getting a little creative here and I wanted to use something different other than, I'm going to try and move this out the way because this is supposed to be oxygen. And I can't move it out the way either. So, all right, let's just quickly pause it. All right, fixed it. Oxygen, right? So you're gonna divide both of those by that lowest one. And so what's going to happen is When you divide something by itself, you're going to get 1, which is great. The other one's going to be above 1, right? And so it might be a whole number. It might be really close to a whole number. It might be halfway to a whole number, right? So the objective is to get your empirical formula, which is whole numbers. So you can round up or keep the number the same if your number is within 0.19 of a whole number. So, for example, if it's 1.81, that's close enough to 2 where you can just round to 2. Something like 3.19 would be rounded down to 3 because you're close enough to 3. If it's a greater distance from a whole number, you're going to have to multiply both numbers by some factor, 2, 3, 4, 5, to get close to a whole number. So if you look here, we can kind of tell 1.5 is about halfway through a whole number, right? So if we multiplied by 2, that'd be close to 3, right? So let's try multiplying by 2, which we did here, 2 and 2. So once we multiply, you have to multiply both elements. You cannot multiply one, you have to buy both. So we did that. We got 2 and 3.084. Now, oxygen is close enough to just round down, and that's what we did here. We just rounded down to 3. So this is now our empirical formula. All right, let's give it a go. We're just going to do another kind of example here, and then we're going to, yeah, we're going to do a couple examples. Let me change a few things first. Okay, back on track. So we've changed a few things here because I forgot to change those. All right. So 28.17% carbon. That's what we're starting with now, and 71.83% oxygen. All you have to do here is change the sign to grams. We can do this because if you have 100 grams of something and you take 50%, that's 50 grams, right? So 50 grams is 50%. Sorry, 50% is 50 grams. 21.5% is 21.5 grams. So just change it to grams and we're good. All right, next step, change to moles using the periodic table, right? Let's circle this. Just again, from periodic table. You're going to write it with the letters and the little subscripts. You're going to divide both of them by the lowest number. This was the lowest moles, so we're going to divide both by that same number, which gives us 1 and 1.913. And just going to round that to C102. We didn't have to multiply anything this time because it was close enough to round, right? It was 0.19 of a whole number. All right, we talked about this. Let's give it a whirl. What is the empirical formula of a compound if the sample contains 0.13 grams of nitrogen and 0.370 grams of oxygen? Let's try that out. So molar mass from the periodic table. Right? Nitrogen is 14.01 grams per mole. Oxygen is 16.00 grams per mole. All right. Well, we're not starting with percent. We're starting with grams. So all we have to do is convert that now. So 0.130 grams of nitrogen times, right? Since grams are on top, we need grams on the bottom. So 14.01 grams of nitrogen to 1 mole of nitrogen. Here is 0.370 grams of oxygen. And we have 16.00 grams of oxygen to 1 mole of oxygen. All right, so let's try that. Let's do the math. I'm going to break out our digital online calculator. So 14.01 divided by, let's see what number that is. Oh, no, sorry, 0.130, sorry. Point, third time's the charm, 0.130. This works with my tablet. Oh, it does. Divided by 14.01. Cool. 0.009279. 0.009279. 9279, and that's moles of nitrogen. Oops, sorry. Oops. Where are we at? All right. 0.370 divided by 16. Do it over here. 0.370 divided by 16. 0.023125. 0.023125 moles of oxygen. 0.23125. All right. So now we're going to write it again like this. N 0.009279. Oxygen 0.023125. All right. Then we're going to divide both by whatever's lower. 0.009279. 0.009279. Let's do that. Well, we know that's going to be N1. Let's figure out what this other one is. 0.023125. We're just going to divide that by 0.009279, maybe? 9279. All right, cool. So then we're going to hit enter, and we got 2.49. Now that looks like it's almost halfway to 3, right? So 2.492, I'm going to write that here. 2.492. All right. So since this is very, very close to 2, sorry, to 2.5, we're going to multiply by 2 to get it to almost 5. So let's try that. So it's going to be, we'll say multiply by 2, multiply by 2, N2, O. Let's do that. And let's multiply this by 2. And we got 4.984. 4.984. And we'll just put a brackets here, times 2 to get to whole number. My computer's lagging a bit. All right, so that's going to be, now we're just going to round because it's very close to 5. N2O5. Oops. That's our empirical formula. All right. All right, let's do a last one here. What is the empirical formula of a compound containing this many percent? And now there's 3 things, so it's getting a little more complicated. Let's check it out. All we have to do now is add a third element. Then we go to the mass, then we go to the moles, and then we just combine them here, and everything's exactly the same. So let's try it. Molar mass, carbon, 12.01 grams per mole. Hydrogen, again, these are off your periodic table, 0.008 grams per mole. Oxygen, 16.00 grams per mole. All right. So let's take care of that. Percent of first element. Again, we're just going to change the percent to grams. So it's going to say 40.0 grams of carbon. That's going to be, oh, sorry, that was supposed to be percent. Let's just do it step by step so no one gets lost here, especially me. Percent carbon, we're just going to say 40.0 grams of carbon. We're going to say 6.71% hydrogen. Well, that's going to be 6.71 grams of hydrogen. 53.28 gram. Oops, sorry, I keep saying percent oxygen. That's going to be 53.28 grams of oxygen. All right, so now we're going to have to change these to moles. So this is now 12.01 grams of carbon per 1 mole of carbon, 1.008 grams of hydrogen per 1 mole of hydrogen. And this is 16.00 grams of oxygen to 1 mole of oxygen. Let's do that. Let's see what cancels out. I don't think I did this last time, but we're going to do, let's see here. The grams of carbon cancel out, top and bottom. Grams of hydrogen cancel out. Grams of oxygen cancel out. We're left with these moles, which is great because that's exactly what we were trying to do. So let's now do the math. So 40 divided by 12.01. 40 divided by 12.01. 3.331. 3.331 moles of carbon. 6.71 divided by 1.008. 6.71 divided by 1.008. 6.657. 6.657 moles of hydrogen. 5328 divided by 16. 5328, oops. 0.28 divided by 16. All right, 3.33. So we're looking good. Because it looks like it's going to be a pretty easy number to work with. C, I'm going to write it like this. This is one of my favorite parts about this because it's very visual and it's harder to get lost, I think, if you have it written this way. You can put it all over the page. You can do whatever you want. I just prefer this way, so I'll let you decide. We're going to divide by the lowest, which is the oxygen, right? Because 3.33 and 3.33. Well, you look at this, this is going to be C1. Let's do H. Oops, sorry. 6.657 clear. 6.657 divided by 3.33, 1.999. So H, 1.999. 1. Let's actually do the other one. 3.331. It's going to be the same, but 3.331 divided by 3.33. Just curious. See, that's just 1.000. So here we go. We're just going to round. And it becomes C1H2O1. That's our empirical formula. All right, that's it for today. I will catch you next time. And yeah, good luck. Work on the stuff, study hard. You can do it. Just takes a lot of work. All right, I'll catch you next time.